Let us continue the discussion on the Kelvin, Helmholtz and Rayleigh-Taylor instability. In the previous couple of lectures, we have basically been looking at the problem of stability of a shear flow as shown on your screen. The velocity has a discontinuity at z is equal to 0, and the velocities above and below the interface are u2 and u1 respectively. The densities of the two fluids are also different. They are ρ2 and ρ1. And we also have gravity and surface tension in the problem. So we have all the key ingredients to look at a variety of interesting special cases. Now, we first wrote down the governing equations in using the velocity potential. The key governing equation is the Laplacian of the velocity potential. We also use the unsteady Bernoulli equation to get the expression for the pressure, and finally we wrote down the normal stress balance boundary condition. We linearized all the quantities, especially the velocity potentials, by assuming a simple form for the perturbation, where we said that the total quantity of the total velocity potential is equal to the base quantity plus a fluctuation quantity, and the fluctuation quantities are all shown with the prime notation. And then we wrote down the linearized equations in the previous lecture. We then employed the normal mode analysis for the linearized equations. We finally got a simple result for the perturbation velocity potential. The perturbation velocity potential was found to just decay exponentially away from the interface. The amplitude or the decay, the amplitude of the eigenfunction, that's A1 and A2 on both sides of the interface, were expressed in terms of the perturbation for the interface position. This is where we ended the previous lecture. What we are now going to do is take advantage of the last equation that we haven't used yet, which is the normal stress balance. We will use the normal stress balance equation and then determine A1 and A2 in terms of eta, and that will give us the dispersion relation. Let us continue with the analysis. Where we left off, we have equation 18, which gives us the values of A1 and A2. This A1 and A2, as I said, has to be substituted in equation number 13. Let's start with this. Substituting A1 and A2 into equation 13 gives us the dispersion relation. That is S as a function of K and L. That's what we're looking for. Let's basically calculate in the expression for the normal stress boundary condition. We have to calculate a few quantities, that is del phi 2 by del x, del phi 2 by del t, and so on for the for 1 as well. Let's calculate some of these quantities separately. Del phi 2 by del x now essentially becomes del by del x. This is a prime, sorry. This now becomes a2 e power minus mz times e power I kx plus ly plus st, and remember this has to be evaluated at z equal to 0. This simply becomes I k a2, because it's a derivative with respect to x. Exponential of ikx simply becomes ik times the rest of the exponential terms, that is kx plus ly plus sigma t. Similarly, we have to evaluate this quantity as well, del phi 2 by del t, and this simply becomes S a2 e power I kx plus Ly plus st. There should be st, sorry, correct that. That's st. Okay, now let's substitute in the equation. What we now have is rho 2 times u2 times ik a2, that is what we have is u2 times del phi 2 by del x, that's the first term, plus del phi 2 by del t, that is sa2. Now finally we have g times eta, that just becomes g times eta hat. This quantity has an exponential of I kx plus Ly plus st. That's what is sitting outside. Then we have minus rho 1 times u1 times ik a1 plus sa1, the equivalent terms. And finally we have, on the right hand side, we have minus gamma times eta xx. Eta xx simply becomes, oh, I shouldn't forget the exponential terms. Eta xx simply becomes minus square eta hat, and eta yy becomes minus L square eta hat times exponential of I kx plus Ly plus st. I can cancel out the exponential terms on both sides. I also can recognize that this quantity here is minus m square of eta hat, where m was defined as m square is k square plus L square. Therefore, if we simplify this, we simply get rho 2 times S plus ik u2 of a2 plus g eta hat minus rho 1 times S plus ik u1 of a1 plus g eta hat is simply gamma m square eta hat. Now, using the expressions for a1 and a2 from equation 18, and what was equation 18 for us? a1 was just S plus ik u1 times eta hat by m. Let's substitute a1 and a2. I will simply get rho 2 minus S plus ik u2 whole square plus mg. I've done some simplification here. Minus rho 1 S plus ik u1 whole square plus mg. This is m cube times gamma. Note that we have a 1 by m in 18, expression 18, eta hat by m. I have multiplied throughout by m, therefore the right hand side becomes m cube gamma and just g becomes mg. Eta hat itself cancels out. We want eta hat to be non-zero, otherwise we would end up getting a trivial solution. The interface remains flat. Okay. Now you can clearly see that this is a quadratic equation in S, and we can rearrange it to get the following. Rearranging, what we get is S square plus S times 2ik rho 1 u1 plus rho 2 u2 divided by rho 1 plus rho 2 plus minus k square rho 1 u1 square plus rho 2 u2 square divided by rho 1 plus rho 2 minus mg times rho 2 minus rho 1 by rho 1 plus rho 2 plus m cube gamma by rho 1 plus rho 2 is equal to 0. This is a quadratic equation. There are one or two more steps that we have to do to go from the previous step to the current step. I would like all of you to try and verify that you are exactly getting the same result. So this essentially becomes, let's call it as A, so that we can write it in a compact notation. What we now have is S square plus AS plus B equal to 0. This is my dispersion relation. It tells me how S varies as a function of the wave numbers K and L. It also tells me what is the dependence of S on the velocities u1 and u2 and the densities rho 1 and rho 2. Now it's a simple quadratic equation. Therefore, the general solution would be S is minus A plus or minus A square minus 4B by 2. That's my general solution. Let's first write down the general solution, and it's a little some simplification has to be done, but let's write it down first. S would be minus A, that's minus 2ik rho 1 u1 plus rho 2 u2 by rho 1 plus rho 2. This divided by 2, so essentially this 2 cancels out, minus ik plus or minus, I have a thing in the square root here, b square, that is minus k square rho 1 u1 plus rho 2 u2 whole square by rho 1 plus rho 2 whole square minus 4b. That 4b will that 4 cancels out to the denominator 2, and we have minus b. That b minus b would be just plus k square of rho 1 u1 square plus rho 2 u2 square by rho 1 plus rho 2 plus mg of rho 2 minus rho 1 plus rho 2 minus m cube gamma by rho 1 plus rho 2. This is square root of the whole thing in the bracket. So that's my expression for S, and as you can see there are too many terms here, but we can do some simplification here. We can combine the first two terms that I'm highlighting. These two terms can be combined. What we do is essentially for the second term we multiply and divide by rho 1 plus rho 2, and therefore the numerator can be combined and certain terms get cancelled. So we simply get, upon simplification, and I would like all of you to try out to simplify it yourself and verify that the answer that you're getting is matching with the solution that I'm getting. Upon simplification, we get minus ik rho 1 u1 plus rho 2 u2 divided by rho 1 plus rho 2 plus or minus k square rho 1 rho 2 by rho 1 plus rho 2 whole square into u1 minus u2 whole square minus mg rho 1 minus rho 2 by rho 1 plus rho 2 minus m cube gamma by rho 1 plus rho 2. This is my final result that I have. So whether the flow is going to be unstable or stable is going to be dependent on the magnitude of the term in the bracket. So if the magnitude term is positive, then the real part of S will be positive, and you can have an instability, right? Well, instead of looking at the full-blown equation, let's look at various special cases, because even though the expression is very big, sometimes it's useful to get better we'll get better physical insight if we look at special cases, so that the essential physics is highlighted in those cases. So let me again write it down. So what we have is a quadratic equation, s square plus as plus b. And the way we have done this is, if the dispersion relation is s square plus as plus b equal to 0, and we are looking for a simple solution of this for various cases. So for us, A is again 2ik of rho 1 u1 plus rho 2 u2 by rho 1 plus rho 2, and B is minus k square of rho 1 u1 square plus rho 2 u2 square divided by rho 1 plus rho 2 minus mg of rho 2 minus rho 1 by rho 1 plus rho 2 plus m cube gamma by rho 1 plus rho 2. This is what I have for the full dispersion relation, right? Now we know that if real part of S is greater than 0, then exponential of SR of t goes to infinity as t goes to infinity, and this is unstable, where SR is where S is SR plus ISI. SR is the real part of S. So the flow is unstable if real part of S is greater than 0. If the real part of S is less than 0, then we have the flow is said to be stable. And if the real part of S is equal to 0, S is equal to 0, and imaginary part of S, which is SI, is not equal to 0, we have oscillatory solutions. And these oscillations will go on forever because there is no viscosity, so there's nothing to damp. So we now look at special cases. So the first one is a case where the velocities are completely 0, u1 is equal to u2 is 0. If we do this, then if you look at the constants a and b, a essentially becomes 0 and b simplifies to minus mg rho 2 minus rho 1 by rho 1 plus rho 2, and plus m cube gamma by rho 1 plus rho 2. Correct? So the equation that we have is s square plus b is equal to 0. That's the dispersion relation, and therefore s square essentially becomes minus b, and what is that? It's just mg of rho 2 minus rho 1 by rho 1 plus rho 2 minus m cube gamma by rho 1 plus rho 2. This is my expression for S, and therefore S itself becomes plus or minus square root of this quantity, rho 2 mg minus m cube gamma by rho 1 plus rho 2. That's the expression for S, right? Now we have a system where now we have a flat interface, practically flat interface, and on top of this flat interface we have tiny undulations are created, and we have the density above is rho 2, the density below is rho 1, and gravity is pointing in the downward direction, right? So you can clearly see, if let's basically give this a label, let's call this as we have not given labels to some of these equations. The full dispersion relation, we'll call it as 19. The special differential equation, the simple form will give a different label, 19. This is 20 and 21. So now we have basically got the dispersion relation number 22, which is valid for the system that is shown. You have an interface which is perturbed. You have rho 2 above and rho 1 below, correct? Now, if rho 2 is less than rho 1, right? If the upper fluid is lighter, then S is nothing but plus or minus the square root of a quantity which is always negative. Because notice that it is rho 2 minus rho 1. If rho 2 is less than rho 1, the first quantity is negative. The second quantity is anyway negative, which means S is plus or minus I times Si, where Si is nothing but purely the imaginary part of this quantity, which is magnitude of rho 2 minus rho 1 by rho 1 plus rho 2 mg minus m cube gamma by rho 1 plus rho 2. It's just the magnitude of this quantity. So it's purely oscillatory, right? In this case, flow is purely oscillatory in nature, and that's not surprising, because if the density above is lower than the density below, then clearly if you make any undulations, let's look at the physical mechanism. This was my original interface. If you make any undulations to the interface, then in these regions, now you have filled these regions with a density of rho 1, but originally it was surrounded by a region where the density is rho 2. Now remember rho 1, so if rho 1 is greater than rho 2, then this density perturbation, this region has a excess density, rho 1 is greater than 0. On the other hand, where you create a depression, the delta rho is actually less than 0, because originally it was basically rho 1, but now you filled it with rho 2, which is a lighter fluid, and therefore the excess this particular region will have a delta rho, which is the density difference is less than 0, and again in this region you have a density difference which is greater than 0. So if the density difference is greater than 0, gravity tends to pull it downwards, right? Gravity restores the interface shape. Notice that the surface tension term is negative, and it does not change with the sign of the density. It's always negative. That's understandable again, because any undulations that you create on the surface will lead to an excess surface area, which is undesirable. So essentially, the surface tension, if you the moment you perturb the surface, you are paying a penalty as far as surface energy is concerned, and therefore surface tension will try to kill the interface perturbations. It will try to basically bring it back to its original horizontal state. That's what surface tension will try to do. In this case, gravity is assisting it by when the fluid above is lighter than the fluid below, right? What about the other case, where if rho 2 is greater than rho 1? So upper fluid is heavier than lower fluid. Intuitively, you would expect this flow to be unstable, because if heavy is sitting over light, then certainly you would expect the heavy fluid to just collapse. Let's see if this is actually valid. So this is my interface, original flat interface. Let's say if I create a perturbation, now because rho 2 is greater than rho 1, this perturbation here is delta rho is less than 0, and this perturbation is greater than 0. So the physical explanation is that if you create a crest and a trough, the crest becomes lighter, and when it's lighter, it tries to rise up even further. The trough, on the other hand, is heavier, so it basically sinks further. So that basically is the mechanism for this instability. But is it true? Are all kinds of waves unstable? Is it always true? Is there a stability criteria that we can come up with? So if you basically say that rho 2 is greater than rho 1, if you look at the equation 22 that we have, this would essentially mean flow is unstable if the quantity under the square root in 22 is positive, which is rho 2 minus rho 1 divided by rho 2 plus rho 1 times g times m times g minus m cube gamma by rho 2 plus rho 1 is greater than 0. That's what we have. Now clearly you can make some simplifications here. For example, the bottom is always, this is always positive. You can also cancel out 1m on both sides. So we now have unstable if rho 2 minus rho 1 of g has to be greater than m square of gamma, right? So it is essentially saying that previously we thought if density above is lighter than heavier than the lower fluid, the upper fluid is heavier than the lower fluid, you would intuitively you could say that this flow has become unstable because of the mechanism that I just explained. But that's only true when surface tension is the surface tension is not present, because as you can see in this particular drawing that I've made, while it is true that making a crest will make it even lighter, the trough regions become heavier, but there is a barrier for these perturbations to grow. What is the barrier? If these perturbations are growing, then that is also increasing the surface energy, and surface tension would oppose that. You're increasing the surface area and surface tension would oppose that. Therefore, there is a cutoff criteria. The cutoff criteria is as follows: rho 2 minus rho 1 of g, this density difference has to exceed a particular threshold. You can also look at it in another way. The quantity m square if it's lower than this, rho 2 minus rho 1 g by gamma, then I have m is, when it is less than this quantity, g by gamma, so the wavelength will be 2 pi by k, sorry, 2 pi by m. So this is gamma by rho 2 minus rho 1 into g into 2 pi. This is what I have, right? Now, notice that this exactly is basically the capillary length. So it says that if lambda is greater than, did I miss? Okay, sorry. If lambda is greater than, oh, there's a 2 pi. If lambda is greater than 2 pi LC, then flow is unstable. So the idea is the following. So let's say we have a flat interface. You can create all kinds of perturbations on it. Let me make that flat. You can incorporate all kinds of perturbations on it. So let's say we create tiny perturbations on it. In that, when you create a tiny perturbation, you are paying a very heavy price in terms of the surface area. The surface area for such a surface is so high that surface tension would not favor this growth of this kind of a wave, and these waves are stable, right? So this is a case where lambda, this is a case where lambda is actually less than 2 pi LC. On the other hand, let's consider an interface. My original interface is flat. I have considered an interface where the wavelength lambda is large. So this is for lambda greater than 2 pi LC. And when this happens, the wave will grow. The wave will grow because gravity is going to start dominating at this length scale. You are well above the capillary length. And remember, capillary length is the length scale obtained by where the surface tension and gravitational forces are in balance, right? So what is the moral of the story? The moral of the story is surface tension stabilizes the Rayleigh plateau instability at small scales. At small scales or small wavelengths or large wave numbers. So if you create a very tiny fluctuation on the surface, then of very small wavelength, then such fluctuations would be immediately would become, the system is stable, and what you expect is or rather it's oscillatory, because you've created an undulation. These waves just keep oscillating forever. But of course, in a realistic system, these oscillations cannot persist forever. What we have is a viscous damping that occurs. So let me quickly recap what we have done in today's lecture. We started by looking at, we completed the analysis of the dispersion relation. We derived a general dispersion relation by finally using the normal stress balance. And after deriving the general stress equation, dispersion relation, it turns out to be a simple quadratic equation. And for the simple quadratic equation, exact solutions can be found. That is, the exact solution is equation 19. But as you can see, equation 19 is too cumbersome. It's difficult to extract necessary insights, where we can highlight the role of each and every force, each and every term in the problem. It's difficult to understand it if you look at the full-blown equation 19. So instead, start looking at special cases. Special case 1 is where there is no motion, no velocity at all. This is the Rayleigh-Plateau case. I'm calling it case because we've not necessarily that has to be unstable. So Rayleigh-Plateau instability occurs when you have a heavier fluid setting over a lighter fluid. So the heavier fluid tends to sink down. But what we find is that there is a critical wavelength. Only when you are above the critical wavelength is 2 pi ln c. Only when you are exceeding the critical wavelength, then does the flow become unstable. All right. So what we will be doing in the next lecture is to look at the so-called Kelvin-Helmholtz instability. So we've looked at the Rayleigh-Taylor instability, a Rayleigh-Taylor case. We will look at the Kelvin-Helmholtz instability. Again, we'll make some simplifications. In the Kelvin-Helmholtz instability, the driving mechanism for the instability is the difference in the velocities u1 and u2. So if we want to keep the focus primarily on the shear that is present in the problem, we will basically assume that the density is just constant rho naught when we do the analysis for the Kelvin-Helmholtz instability. So I'll see you in the next lecture. We'll complete this discussion hopefully by the end of next lecture. Thank you.